In this video, we're going to describe how sound waves spread out and get quieter. In order to understand how waves spread out, we need to remember that waves propagate with some velocity. And these figures help us see that again. This left figure shows waves caused by a ripple centered around some disturbance. And again, remember that ripples are circular transverse waves, so they aren't a great model for sound, but I think this picture is really interesting because you can see that each ripple is smaller than the ripple inside of it, which suggests that waves spread out and shrink, and that might be a good explanation for why sounds get quieter as you get further away. Now, like I said, ripples aren't a great model for sound waves because they're transverse and are two-dimensional. So this picture on the right is supposed to help you visualize a longitudinal wave in 3 dimensions. It shows regions of, you can imagine, compression and rarefaction spreading out around some central point and getting less intense in color, which you can imagine as being quieter. So if we want to figure out how much quieter a wave gets as it spreads out, we can make a pretty simple mathematical model that helps us understand it. First, we imagine there's some power source that's creating waves. That's PTX in this picture, which stands for transmit power source. Waves spread out around PTX spherically, so the transmit power gets spread out evenly over a sphere. That means the intensity, or power per unit area, at the sphere's radius is given by I of r is equal to PTX over 4 pi r squared. Now, just for the sake of converting between units, we need to note that intensity is equal to the local pressure times the flow rate, which you can get from dimensional analysis. Intensity is watts, which are Newton meters per second per unit area, and pressure is newtons per unit area, and flow rate is meters per second. So you can see multiplying those two quantities together gives us the same units as intensity. Now, it turns out we're going to need to be able to convert between units of intensity and pressure and velocity. So we need to set up an equation that lets us do that. We can actually figure it out pretty easily based on dimensional analysis. Intensity has units of watts, or Newton meters per second per meter squared. Pressure has units of newtons per meter squared, and flow rate has units of meters per second. So we can see if we just multiply the pressure and the flow rate units together, we get the intensity units. In addition, there's a relationship between pressure differences and flow rate at any point in the fluid, which is a property of the medium, and it's called the acoustic impedance. This property is a little bit like Ohm's law. Pressure is sort of like voltage and velocity is sort of like current. So we're going to call our acoustic impedance Z0 and substitute U is equal to P over Z0 into our second equation here to find that our intensity is equal to the pressure squared divided by the acoustic impedance. We care about this because a microphone that we use to measure stuff in the water is going to report voltages, and we need to be able to relate that voltage to the power in the water. And though we're not going to keep track of exactly every term because you can often back some of them out with calibration, that relationship between voltage and power is one that matters. So specifically, with that in mind, what we know is that the voltage on the microphone is proportional to the pressure in the water, because we're told that by a datasheet. And we know that pressure is proportional to the square root of intensity from our second equation here, I is equal to P squared over Z0. And finally, if we substitute our first equation in for I of r in our third line, we can see that the microphone voltage is proportional to the square root of the transmit power divided by r, the distance away we are from PTX. So the big takeaway from this analysis is that your microphone voltage is proportional to the square root of your transmit power, and it's inversely proportional to the range that you are away from your transmitter. So in general, you expect you'd expect an Rx power, a received power versus range curve to look like 1 over x. Now we've been talking about waves getting quieter because they're spreading out, but waves can also become quieter by being absorbed into their medium. I mean, specifically, this is different than spreading out because the wave power, instead of becoming small, actually goes away. It turns into heat. And this absorption process is called attenuation. Now, attenuation results in an exponential loss of power with distance, which is actually much worse than the previous slide, where our power only fell off as 1 over distance squared. However, the coefficients for this loss in the ocean tend to be about 1 decibel per kilometer, because water is not a very lossy medium. And because the ranges we work at are a few meters, this usually isn't a problem for us in the 80. So in summary, the major takeaways from this video are that the power in a wave is spread out evenly over a sphere, which means that the voltage at your microphone is proportional to the square root of the transmit power and inversely proportional to range, to the distance you are away from the transmitter. Also, waves can lose power from attenuation, but sound waves in water usually lose that over longer ranges than we care about in the 80.